that can execute the instruction, and eventually that will give you the idea how to design the CPU. Okay, how to design the CPU, because our main goal of midterm syllabus is to design the CPU. We want to learn how to design the central processing unit. If you look at the central processing unit, you see, I think the entire component CPU is divided into main parts. Let me just write it. Can I write it over here? Let me use the PowerPoint slide. I think. Okay. You see, if you look at the CPU, let's say this is the CPU. Entire CPU is divided into n parts. One component is called data path. And another component is called control unit. So this is the entire CPU, central processing unit. Our job today, we are going to simulate data path. So if you want to simulate data path, you need to understand first what is inside data path. So let's see. First thing comes that is inside the data path is registers. Okay, registers. What are the registers? Registers are the temporary storage inside the CPU, like it's a memory or temporary storage inside the CPU to store data and instruction. So inside the data path, it contains the registers. Another component, it has the arithmetic logic unit. It can perform arithmetic and logic operation. And all the components, these registers and LU, they are connected by some wires. Okay, this can be point-to-point connection or multi-point connection. Point-to-point connection, point point-to-point connection. Okay, these connections are very important to understand. Point-to-point connection and multi-point connection. So this is the way different components that get connected. Okay, multi-point. Okay, so the components inside the data path has wires that connect different parts. It can be point-to-point connection and multi-point connection. What is point-to-point connection? Let me explain with the picture. Okay. This is the memory data path graphical. This is the main memory, and this is the registers. Memory address register, program counter, memory buffer register, accumulator register, input register, output register, instruction register. This is multi-point bus system. This is the multi-point bus. Multi-point, okay. You see, in multi-point bus system, many devices can be connected. You see, main memory is connected to the multi-point bus, memory address register, program counter, memory buffer register, accumulator register. Different components can be connected to the multi-point bus. Okay. And this is the point-to-point bus. point-to-point bus only between these two components, like in between memory buffer register and ALU. Okay, point-to-point bus system. Between memory buffer register and accumulator register, point-to-point bus. Between ALU and accumulator register, point-to-point bus. So some connections are point-to-point and some connections are multi-point. Why we give point-to-point connection? Because operation or data transfer between these two devices become very fast and simple. Okay, it improves the performance. Between MBR and SC, point-to-point connection. Between SC to ALU, point-to-point connection. So data transfer between these devices become faster and efficient and simple. But for all the devices, you cannot do point-to-point connection. It's not possible. So for another device, we have used multi-point bus system. Okay, this is the married data path shown graphically. Now, I'll play a small video, okay, to give more explanation on this topic.
In this video, we're going to describe very quickly what is known as the MARI architecture. This architecture is a fairly simplified microprocessor so that we can understand how the different registers and components work. The first component we're going to depict here at the top, it's going to be the memory. Now, MARI has a memory which has a total of 8 kilobytes of information. However, the special feature about this memory is that it contains 2 to the 12 cells, but these cells are 16-bit addressable. What it means is that I do have 2 to the 12 cells, but each one of these cells, you can visualize it like this, contains precisely 16 bits. In other words, every time I read a data from this memory, I receive 16 bits of information, and every time I want to write a piece of data in this memory, I have to provide an address and 16 bits of information. The REST architecture is comprised of 7 registers. The first one we're going to depict here is what we call the MAR, or Memory Address Register. As the name says, this register is in charge of storing the address of the data we want to either read or write from the MARI memory. Next, we have another register, which we call it the PC or program counter, which holds the address of the instruction that is being executed or the instruction that is going to be executed next. As you can see, these 2 registers over here hold addresses, and therefore the size of these registers is 12 bits, because the number of bits needed to address this memory bank is 12 bits as well. Next to the program counter, we have a third register, which is called the Memory Buffer Register, or MBR. MBR, on the other hand, it's going to be a register that is going to contain data that we either store in memory or we retrieve from memory. And therefore, the size of this register is not going to be 12, but 6 bits. Next, we have probably the most important register in our architecture. It's called AC, and is known as the accumulator. The accumulator will be the register we use to perform operations and store temporary results. Now, the interesting part here is we're going to have as well a combinational value, which will be in charge of performing arithmetic and logic operations, as we saw in previous examples. We have 2 additional registers, in and out reg, which will be used for input and output operations, and a final register, which will be IR, which we will call the instruction register. Now let's look, now that we have introduced only the names of these registers, let's see how are they connected to each other. And the crucial observation here is that this architecture, all these blocks are connected through a bus that we are depicting like this, which contains address and data bus. And the connections of these blocks to this bus are all of them like this. MAR is connected like this as well. PC program counter can write on the bus or read from the bus. Same thing for MBR. Same thing for the accumulator. What this means is that all these registers can write on that bus or read data from that bus. And therefore, we don't need so many point-to-point communications. Okay. Additionally to these connections, we still need to see how the data comes in and out of the ALU. Now, this architecture, it's going to rely mostly on the data that comes from memory and is stored in MBR. Processing the operations will be in the ALU, and storing the results will be on the accumulator. Therefore, we're going to have in this architecture these additional specific connections. So we'll have the possibility of loading data from the MBR to the accumulator and vice versa. And the ALU will be capable of taking two MBR and accumulator and store the result as well on the accumulator. So if you look a bit carefully here, these two registers, they have to be controlled in a way that even though they have two possibilities to read their data, in the case of the accumulator we have three, there has to be some control logic that has to decide at all times if the accumulator is going to load whatever value is in the bus, whatever value comes from MBR, or whatever value has been produced by ALU. Now the communication of all these blocks to the bus, we're going to enumerate them like this: 1, 2, 3, 4, 5, 6, 7. You have to remember that only one of these connections can be active at the same time in order for the value to propagate to the entire bus. Remember that a bus is a collection of signals such that if two connections are connected at the same time, that produces an unstable value all around the bus. So we need a policy to access the bus such that out of these 8 connections you see here, only one of them is active at any point in time. So now let's go over again the size of the registers. We have these two registers, MAR and PC. They have memory addresses, represent like this, and therefore the size is 12 bits. They have memory addresses because this is when the register that we're going to use to store the address to access memory, and the program counter is always pointing to the address of the next instruction we have to execute. MBR and AC, on the other hand, will be processing data. Now the data comes from this memory, and we know that this memory is 16-bit addressable. In other words, it has 2 to the 12 cells, each of 116 bits. These cells, when they are read from memory, they'll be stored in the MBR, and the results will be processed by ALU and stored in the accumulator, and therefore we have 16 bits here for data processing. In this architecture, the additional 2 registers, in-reg and out-reg, are used for input-output operations, and they are based on the representation of letters, and therefore they will have a size of 8 bits for input and output. 8. And finally, this register, which is the instruction register. The instruction register, these instructions will come from memory as well, and therefore, from the point of view of the size, it is similar to the accumulator and MBR, and therefore, you'll have also 16 bits. So, to summarize, what we have here is a very simple architecture. This architecture is based on this first block, which is the memory with data and instructions. And then these registers over here will be used to store addresses for the case of MAR. A counter, what we call the program counter, next instruction to be executed. The data that is being either read from memory, MBR, the accumulator, operations will always store the result there. Input data into the computer, output data into some sort of peripheral or device, and where we store the instruction being executed, instruction register. In this video, we're going to describe very quickly
So we have seen the explanation of the data path, and now can you tell me what is the advantage of point-to-point bus and what is the disadvantage of point-to-point bus? At this point, bus connect different components inside the data path. Can anyone tell? Yes, what is the advantage? Anyone can have some idea or think about the advantage of point-to-point bus? Let me tell you the next scenario. Suppose your university is open and you want to come to your university. Okay, what we see every day in the morning when students come to the university, huge traffic jam. Okay, huge gathering. Traffic gets slowed down. It takes time to come to the university because many students come to the university at the same time. So we can consider the path the students take to the university is the multi-point path, multi-point bus system, because many students share the same road, road to go to the university. It is a multi-point system. Many users use the same resource, same path. But what happens? Suppose you have your own road, okay, let's separate road or path from your home to the university, okay, like point-to-point road or bus system. No one, only you can use the road. No other people can use the road. Because when the Prime Minister moves on the road, only the car of the Prime Minister is on the road. No other people can use the road. Okay, it is like point-to-point bus system. So what is the advantage? When only one person uses the road, no other person can use the road. Fast operation. You don't need any traffic police and traffic light. No rules and regulation. No complexity. Okay. So faster operation and simple design. Okay. That's the advantage of point-to-point bus system. But the main disadvantage, we cannot give separate path for every student to the university. Is it possible that you have a separate path, your friend has another path, another friend has another path? Let's say there are 40 students in the class, there are 40 different paths or road to come to the university. There are 10,000 students in the university. So 10,000 different paths for 10,000 students. Impossible. Okay. So for all the students, you cannot keep point-to-point connection. Only when it is really beneficial, okay, improve the performance, we give the point-to-point connection. Okay, for faster operation. Otherwise, we give multi-point connection. So that's the design of the data path. Today we are going to simulate this one. And if you look at the numbering, you see, when there is a point-to-point connection, they don't need any identity or number or name. Like transfer between MBR and ALU, there is no name. Okay, they don't need any name or number. They can do transfer directly because no other people or no other device is sharing their point-to-point connection. But this is multi-point bus system. Every device has a name or number, and only one device can be activated on the multi-point bus system. Because it is in our like road, Puratli road, many students at the same time share the same road. You, your friends together, many friends, all of you hand in hand can walk on the road and come to the university. But inside the computer multiple bus system, it's not possible. Because inside the computer wire, okay, who are the people travel? High voltage and low voltage, 0 and 1. These 0 and 1, they cannot work in hand together like a friend. Okay, if they hold their hand together, then 1 will be 0 or 0 will be 1. Okay, that means data will get corrupted. Okay, so inside the computer, only either 0 will go or 1 will go. That's why only one device can use the multiple bus or can send information to the multiple bus at a time. But other device can receive the information. This type of policy is called master-slave configuration. Okay, in multiple bus system, we use a policy called master-slave configuration. Only master can send the information, and all other devices become slave. They can receive the information. So any device want to send the information, he become the master. Okay, and all other devices become slave. So there is only one master at a time. Okay, and there are rules and regulations. It is called bus arbitration technique. In chapter 4, we'll go in details. There are 4 types of bus arbitration. I think if I go to the slide, I'll just give you the daisy chain is one type. We'll go in details in the theory class. Daisy chain, centralized power, distributed using self-detection, and distributed using collision detection. Okay, so these are the 4 categories of bus arbitration are used to decide which will be the master, and so that he can send the information. Okay. So our job today, we will use a simulator. I have already uploaded the simulator on your post section. If you look at over here, marydp1.jar, and this is the lab sheet, lab 4, and this is the chapter 4 PowerPoint slide. So what you need to do, you download this file. Let's just download it. Okay, so let me check. So as I do, same thing you can do. Let me see. This is the downloads. I think. So I have downloaded the file for the data path simulation. So now what you need to do, just double click the file, but make sure you have Java installed in your computer. If you don't have the Java installed in your computer, make sure you need to download it from the net. And in the lab number 3, we have shown you that process. Okay, so hopefully all of you have the Java installed in your computer, and just double click the jar file, and it will open up the data path simulator. Look at over here. The entire data path is shown over here. Data path contains the main memory, registers, and the connection between them. So this is the entire CPU. This portion is the data path. This portion is the data path. Okay, this portion is the data path, and this is the control unit. Okay, so this is the entire CPU. Control unit send the control signal to control and coordinate the activity of the computer. So data path just a piece of hardware, but the operation of the inside the data path is controlled by the control unit. You see? If you go to the help file, I think it will open up some information about this simulator. The Mary machine environment animates the data path activities that take place within the Mary computer. This simulator traces the execution of an assembled Mary assembly language program as data is moved between each of the registers and main memory. When the value stored in a register changes, the contents of all registers are printed in the trace window. So whatever happens inside the data path, that value again get printed on the trace window. So what is the trace window? This is the trace window. When you load the program, your program will be displayed over here, and this is the trace window. You can see the value of different registers. Running a program, how to run the program? Before you can run a program in the simulator, you must first assemble it using the facilities of the main Mary machine simulator called MarySim that we have done in the lab number 3. Once you have an executable program, load it and run it using the buttons in the main menu bar, okay, of the simulator. To observe the details of the data movement, you can slow down the execution speed using the set speed menu bar button. So let's see where is the set speed menu bar button. This is the set speed menu bar button. You see, if you give more value, your simulation will be more slow. If you give less value, it will be very fast. But we need to see the activity in details, okay? So we'll slow down the simulation. Okay, I have given some value. If you want to make it more slow, okay, see, it will go like a turtle, okay? So you can, if you increase, it will be more like a turtle, okay? So I think this value, I think you can visualize that nicely. Okay. We have noticed that when the speed is set so that execution is very slow, the fetch process of the fetch decode execute cycle can become boring to watch over and over. To relieve this boredom, we have provided a fast fetch mode X button to bypass the delay during the instruction fetch process. So you can faster the simulation by bypassing the fetch process. Okay. While your program is running, components that are involved in a data transfer operation change to a bright color. Okay. So when you simulate, you will see that the components that are involved in that particular process, okay, change to a bright color. The control unit determines when each component will be activated. As you know, only one device can be activated at a time inside the data path. Only one device, because it's a multi-point bus system. So how it is done? Control unit does the job for you. You see? The control unit determines when each component will be activated. As explained in the text, each register has an identifying number. This value determines which register will be read from and which register will be written to. The control unit sets the binary number of each register on the read and write control lines according to the needs of the instruction being executed. The register numbers in decimal are as follows. Instruction register is number 7, out register is number 6, in is 5, accumulator register is 4, memory buffer register is 3, program counter is number 2, memory address register is number 1. The main memory number is 0. So if you look at over here, you see, this is the numbering or name of the different components. When you run a program, you will see how these binary numbers translate into control signals on the control lines. Okay, using the controls on the menu bar, you can run or stop execution. Stop through execution, that means instruction one by one you can execute. Step through one after other you can execute. Okay, not all together. First instruction, so it is called a step through. Okay, you execute the first instruction, one step, then another step is the second instruction. What is the finding we see in the trace window? Those values we are going to put down in our lab. Okay, so we'll go with the process of step through. And for every instruction, we'll create a separate table, as in the lab sheet. Let me just show you the lab sheet. I think, yes, it's a lab sheet over here. If I scroll down the lab sheet, the program that we are going to use for this lab is the very basic program. This is the basic program. Addition of 3 numbers, A, B, and C. Okay, so we are going to use this program to observe the data path operation. So first you need to write the program in the Mary simulator, main simulator, then get the hex file, and then you can load the hex file on the main data path. Just 1 minute. Okay, so this is the program. If you already have the hex file from the last lab, you can load the hex file or binary file. We call binary file, okay? It's the machine code directly to the data path simulator. But if you don't have the binary file of lab 3, then you need to do it again, okay? I'll show you the entire process. I'll show you the entire process for this lab, okay? So this is the simulation and measurement. Enter and assemble the above program in the Mary simulator. Load and run step by step the program in the Mary datapath simulator. In each step, observe the change in the Mary register contents and the corresponding marker. Okay, these are the main things we need to observe. For each instruction in the program, create a table as follows with the corresponding data from simulation. So if you look at the table, for each instruction, already in your lab sheet, a table has been created for you. This is first instruction load A. Okay, and what happens when you execute the instruction? It works like fetch, decode, execute cycle. If I open up your PowerPoint slide, because your lab corresponds to the theory, since we can and it's the theory behind the lab. Okay. Instruction processing flowchart. Okay, your computer works on fetch, decode, execute cycle. This is the fetch, decode, execute cycle. Fetch, decode, execute. Fetch the instruction, then decode the instruction, then execute the instruction. So we can represent this fetch, decode, execute cycle in a flowchart like this. When you perform the fetch operation, you copy the program counter content to the memory address register. Okay, then copy the contents of the memory at address mark to instruction register and increment program counter by 1. Okay, so this is the fetch process. Fetch. So this is the fetch process. Okay, so if we write down the fetch process in terms of a language called register transfer language. This is the language you use to design the instruction of a new CPU. When you want to design a new CPU, you first design the instruction of the CPU. You decide what to do the instruction of the CPU and how to define the instruction for the CPU with a language called register transfer language. We call RTL, register transfer register transfer language. This is the language is used when you first design a new CPU and you define the instruction for the CPU. So this is the first step. When you design a new CPU, the first step, design the instruction. Now, how you design the instruction? By using a language called register transfer language. So if we reuse the register transfer language for the fetch operation, it looks like this. The content of PC get placed in the memory address register. Then from memory, M is transfer memory, this capital letter M is transfer memory and address. So from the addressed location of the memory, You read the instruction and it comes to the instruction register. So this is the register transfer language, okay? Then you increment the program counter by 1. And at each, these are called micro operation. These are called, every step over here is called micro operation. Every line in the register transfer language is called micro operation. Means it is a basic operation. For each micro operation, you must design the corresponding hardware. That's why this lab is very important if you want to design the CPU. Okay. For each micro operation, you need to design the corresponding hardware. So if this gives you the idea what type of hardware should be inside your CPU, like for this operation, and how this done? How this is done? Control signal. Send the control signal. Look at over here. Control signal unit. Control unit will send the control signal, and the value of PC will come to the memory address register. When you will simulate, you will see the operation. Control unit will generate the signal, and the value of PC will come to the memory address register. Okay, so this is the way it works. So these are the micro, and for each micro, you must design the corresponding hardware. And you know how to design the hardware. If you do the digital logic design course, you know how to design the hardware. So just one signal from the control unit, this micro operation will get performed. And as this micro operation get performed, it affects a particular register, like the content of memory address register get changed. You see, the content of PC comes to the memory address register. So in the trace window, this is part of the trace window in the simulator. If you look at the simulator, this is the trace window. In this trace window, this value will be appear. Okay, the value over here, this value that you see over here is part of the trace window. You will get this value from the trace window, and you will put down those value in the lab sheet over here. Whatever you see in the trace window, you will put down those value in the over here. This is the trace part, and this is the micro operation part, register transfer RTM. Okay, this is the micro operation part. So from the simulator, you will have this information. This information you get from the simulator, register transfer, and this is the trace part. Where you get? Okay, it will appear over here. In this portion, in this blank portion, the micro operation will get appeared. So you'll put it down on your lab sheet. And on the trace window, you will get a value of different register, and you'll put it down in the lab sheet. In this way, for every instruction, you need to fill up a table. Like for the first instance load A, from the simulation, we'll fill up this table. Fetch, then decode, then get apply, then execute. Okay. And for the second instruction, add B, add C, store sum. So there are 5 instructions and there are 5 tables. Okay, so this is your lab. So let me just show you starting a demonstration. Okay, and as you do, all of you can do the same thing. Okay, in your own computer, as I do the steps, you follow the same process. So we must need the binary file first. So how to get the binary file? You need to run the Mary simulator, Mary main simulator. Okay, so where is the Mary main simulator? If you go to the post section, if you look at over here, you will find your Mary main simulator already uploaded in the lab number 3. You see, marysim.jar. You see, so download it. If you don't have it in your computer, if you lost it, you can do it again. Okay, just download. It's the Mary main simulator. So let me go to the download folder. Yes. So double click the Mary sim, this file. It will open up the Mary main simulator. In this simulator, first we need to assemble or write our program, then assemble it. So to write the program, you click the file menu, then click edit and type the program. Which program you are going to type? The program that is in the lab sheet. So look at over here. So go to up in the left sheet. This is the program that you need to type. Okay, this is the program that type over here. So let's do it. Mary simulator, and this is the Mary. You can put it like this to be easier to type the program. Okay, so first is origin 100. Why it is origin 100? Because when the Mary simulator or when the Mary computer first get turned on, okay, it reads the first instruction from this location. By default, the instruction pointer or program counter get initialized with the value 100 at the beginning. So we need to load the program at the location 100x. So this is the origin 100. So now type of program load load A add B and now add C store sum. So after adding three variables, you need to store the result at the location sum. Okay. Okay. After store the result at the location sum in memory, the program gets stopped. So halt will stop your program. So this is your main program. Okay. This is the main program. This is the instruction of the Mary that you can find in the Mary instruction list. If you go top of your left sheet, you will find the Mary instruction list. So this is the main program. Now when you write the program in the assembly language, then you can define the variable of the value, like what is the value of A, value of B and value of C separately. So this is the variable declaration. This variable declaration is not the instruction, okay? This is your main program. Now you declare the variable. In assembly language, you declare the variable like this. Variable A, comma, give one space, at least one space, okay, or some space. Then it is a decimal value. Decimal is the assembler directive. It tells the assembler that this value that you are writing over here is a decimal value. Okay, if this value is binary, then you write BIN, binary. If it is in hex, then you write hex, SCXX. Okay, so this is the assembler directive that tells what of the value you are assigning to the variable A. And B, decimal 15, any value you can give. Okay, and C, decimal. You must make sure some students do mistake. A comma, they directly write decimal. Okay, you must give one or more space. Okay, otherwise your assembler will find it is a mistake. So this is value 20, and the variable sum is initialized with 0. Okay, let me do a small mistake. Okay, your assembler is case sensitive.
Hello.
We have declared this value sum like this. Okay, S is capital letter, U and M is a small letter. Let me do it all on capital letter. Let's see what happens. Decimal 0. Finally, this is the end of your program. N is the assembler directive. It tells that this is the end of assembly language program. Okay, now I need to save it. File, go to the save menu, Okay. You need to first select the file of types. This is the extension .mas. That means that it's the Mary assembly language program file. So after selecting the extension, okay, you need to choose, better you need to choose a folder, okay. Let's move to up one level or create a new folder. Okay, create new folder, okay. Let me create a new folder. Let's CSA lab 4, okay. No, not music. CSA lab 4. Yes, this folder. Okay, so we need to better create a folder and save your program over there, because when you assemble the program, it create many files, not only one file. It get list file, okay, it get map file. That's part of the assembly process. Okay, so give a name of your program. It's a lab4 program. And save it. Okay. Okay. If you look at the bottom of the Mary assembler code editor, you see it is displaying the location where your program has been saved. Okay. So after saving the program, you choose the assemble option, assemble current file. Okay. As I have told you, I have done an intentional mistake over here. Look at over here. ASUM, this is the operand, undefined. The assembler is not finding the variable ASUM, because what you have done in your program. Instead of writing AS capital letter and EM small letter, you have written all are capital letter. So these and these are different. That's why your assembler is case sensitive. Make sure you need to keep the name same of the variable. Otherwise, if you use the different letter, small letter, capital letter, they are not same. They are different. It's the symbol table. Okay, so this operand is undefined. Okay, so we need to fix it. So let's fix it. Let's change it over here. See. Okay, now save it again. After correction, we have saved our program. Now again assemble it. Assemble current file. Now if you look at the message at the bottom, assembly successful. Okay, assembly successful. Okay, there's no error, and it has created the machine code. Okay, so what we will do today, we'll load this machine code in the Mary data path simulator. I can close it now safely. We have the machine code. Now we can move to the Mary data path simulator. So come over here and choose the file menu. From the file menu, you just load the machine code. Go to the folder CSLR4, and you see we have the machine code. It says the extension .mex, Mary executable file. That means machine code or binary file. So choose it, open it. So when you open the machine code or program, you see the program is displayed on this window, left side. This is the memory address. At the first location 100 hex, first instruction get loaded. Look at over here. Program counter has the value 100. Program counter has been initialized by the value 100. So it is pointing to the first instruction of the program. Then the second instruction, and third instruction, fourth instruction, and fifth instruction. It's a different variable, and this is the hex value of your entire program. Okay, this is the machine code in binary hex. Okay, this is the machine code in hex. Okay, now is the time to run the program step by step. As I have done before, I have set the speed a little bit slow. Just 1 minute. So if you take a high value in the speed, it will slow it down so that you can easily see and observe what is going on. Okay, so I will not choose the process run. If you choose the process run menu, entire program will get executed, and you will not be able to keep track of different steps. Okay, so we will run the program or we will execute the program step by step. So we'll choose the step option. When you click the step option, it will execute the first instruction. Click a step. So fetch operation. Okay, if you look over here, fetch operation contains these three micro operation, and we'll see that same thing over there. Fetch first step. Then you see, look, you are reading the instruction. Okay, from memory and bring the instruction in the instruction register. Second micro in the fetch cycle. Third micro is the incrementing the program counter. Okay, now you see program counter will get incremented. Okay, it become 101, and all the value has been displayed on the trace window. So after fetching, this is the get operand, and this decode nothing has because this decoding is done by the hardware. Decode the upcode is done by the hardware, so no change in the value in the trace window. Finally, you get the operand from the memory. You get the operand from the memory and bring it in the memory buffer register. Finally, this is the execute part. Place the value in the accumulator register. So this is the load operation. The value from the location or variable A is 10. The 10 will be loaded to the accumulator register. If you look at the accumulator register, this is the value 10 in decimal, and in hex it is A. Okay, so our first instruction execution is complete, and we have got the value 10 in decimal or hex in A is in the hex in the accumulator register, and this is the content of the trace window. I think now is the time you can fill up the table in your lab sheet. If you go down, scroll down to the lab sheet, you see, you can fill up the table over here. You have all the information for the first table. Similar way for every instruction, you fill up all the table. And as you fill up the table, what I suggest, fill up the table with proper understanding. Okay, this is the load operation. It will load the value from the variable A in the accumulator register. The add operation will perform A plus B, and the content of A plus B in the will go to the accumulator register. Now, when you observe in that micro op window, that means your micro operation window over here, it will be displayed. You need to understand what is happening. This is software, and sometimes software can do mistake. Okay, it is not 100% foolproof. If you find that some micro operation is not being displayed or not showing properly, you need to figure out, or not showing this properly. Okay, you need to figure out why it is not showing properly and what should be the right micro. Like for example, if I go to your PowerPoint slide, this is the, I think, trace part of the first instruction, and this is the register transfer. If I go to the next slide, just look at over here. In the execute part, you will find the similarity in the fetch and decode get operand part. Okay, in most cases, some instruction may not have this get operand. Some instruction may have this get operand. This get operand is optional. Okay, fetch, decode, this portion will be mandatory for every instruction. Get operand is optional. It depends on the instruction. Some instruction need the operand, like add, sub, load, they need the operand. Some instruction does not need the operand, like for example, increment instruction does not need the operand. Okay, halt instruction does not need the operand. Okay, so this get operand part is optional. It depends on instruction, but this execute part varies from instruction to instruction. It will be different for different instruction for sure. Okay, different instruction will have different execute part. So when you run the simulation, you see that the same execution of a different instruction, certain mistake. So you need to observe it closely and find out that your simulator is showing the proper value. If you see some problem, then you need to find out, okay, why it is not showing properly, and you need to fix it from your concept or from your knowledge. Okay, look at over here. For addition operation, this execute part will be defined like this: SC plus MBR to SC. So you need to find out the mistake if your simulator has some mistake. Okay, I need to observe those things and put down those value in your graph sheet and in your discussion. Okay, so now is the time for you. Okay, now is the time for you to go. Okay, now is the time for you to do the lab. As I have shown you one step, you follow the process, and in your lab sheet, fill up all the table for your simulation for every instruction. Any question at this point? Any question at this point? Anyone has any other question? So this is your simulator. Get the result from your simulator and fill up the table. 5 instruction, 5 table has been given in the lab sheet. So go to the lab, take a small break. I'll give you the break. After that, how long you want the break? How long you want the break? How long you want the break? Hello? Are you there? How long you want the break? Okay, let me give you, I think I will give you a long break, okay? Let me give you some break, long break, so that you can get relaxed. And after the break, you continue your lab. And when you are done, you can leave the lab, okay? Because the system take care of your attendance. So let us go for the break. So after the break, you can leave the lab, okay? So let me give a long break because it looks like you are feeling sleepy. So let me give you a long break. I think 25 minutes break, okay? Then you continue.
Okay, sir.
When you are done, you can just leave the lab because no other things to do. So today we are going to do lab number 4, computer system data path simulation using Mary simulation software. So So today we are going to do lab number 4, computer system data path simulation using Mary simulation software. So what is the idea behind the lab? The idea of this experiment is to get familiarized with computer system data path simulation, where we will be learning computer system data path simulation using Mary simulator. Second objective, understanding the underlying process when an instruction gets executed. And that's just main idea. But if you go inside of this lab, our main objective of this lab, we want to see how the instruction not only get executed, but it will give you an idea what type of hardware inside your computer. Okay, what type of hardware you need to set up inside your CPU that can execute an instruction, and eventually that will give you the idea how to design the CPU. Okay, how to design the CPU, because our main goal of midterm syllabus is to design the CPU. We want to learn how to design the central processing unit. If you look at the central processing unit, you see, I think the entire component CPU is divided into main parts. Let me just write it. Can I write it over here? Let me use the PowerPoint slide. Okay. You see, if you look at the CPU, let's say this is the CPU. Entire CPU is divided into parts. One component is called data path. And another component is called control unit. So this is the entire CPU, central processing unit. Our job today, we are going to simulate data path. So if you want to simulate data path, you need to understand first what is inside data path. So let's see. First thing comes that is inside the data path is registers. Okay, registers. What are the registers? Registers are the temporary storage inside the CPU, like it's a memory or temporary storage inside the CPU to store data and instruction. So inside the data path it contains the registers. Another component it has the arithmetic logic unit. It can perform arithmetic and logic operation. And all the components, these registers and LU, they are connected by some wires. Okay, which can be point-to-point connection or multi-point connection. Point-to-point connection, point-to-point connection. Okay, these connections are very important to understand. Point-to-point connection and multi-point connection. So this is the way different components that get connected. Okay, multi-point. Okay, so there are components inside the data path as wires that connect different parts. It can be point-to-point connection and multi-point connection. What is point-to-point connection? Let me explain with a picture. Okay, this is the memory data path shown graphically. This is the main memory, and this is the registers. Memory address register, program counter, memory buffer register, accumulator register, input register, output register, instruction register. This is multi-point bus system. This is the multi-point bus. Multi-point, okay. You see, in multi-point bus system, many devices can be connected. You see, main memory is connected to the multi-point bus, memory address register, program counter, memory buffer register, accumulator register. Different components can be connected to the multi-point bus. Okay, and this is the point-to-point bus. Point-to-point bus only between these two components, like in between memory buffer register and ALU. Okay, point-to-point bus system. Between memory buffer register and accumulator register, point-to-point bus. Between ALU and accumulator register, point-to-point bus. So some connections are point-to-point and some connections are multi-point. Why we give point-to-point connection? Because operation or data transfer between these two devices become very fast and simple. Okay, it improves the performance. Between MBR and SC, point-to-point connection. Between SC to ALU, point-to-point connection. So data transfer between these devices become faster and efficient and simple. But for all the devices, we cannot do point-to-point connection. It's not possible. So for another device, we have used multi-point bus system. Okay, this is the married data path shown graphically. Now I'll play a small video, okay, to give more explanation on this topic.
In this video, we're going to describe very quickly what is known as the Marie architecture. This architecture is a fairly simplified microprocessor so that we can understand how the different registers and components work. The first component we're going to depict here at the top is going to be the memory. Now, Marie has a memory which has a total of 8 kilobytes of information. However, the special feature about this memory is that it contains 2 to the 12 cells, but these cells are 16-bit addressable. What it means is that I do have 2 to the 12 cells, but each one of these cells, you can visualize it like this, contains precisely 16 bits. In other words, every time I read a data from this memory, I receive 16 bits of information, and every time I want to write a piece of data in this memory, I have to provide an address and 16 bits of information. The REST architecture is comprised of 7 registers. The first one we're going to depict here is what we call the MAR, or Memory Address Register. As the name says, this register is in charge of storing the address of the data we want to either read or write from the Marie memory. Next, we have another register, which we call it the PC, or program counter, which holds the address of the instruction that is being executed or the instruction that is going to be executed next. As you can see, these 2 registers over here hold addresses, and therefore the size of these registers is 12 bits, because the number of bits needed to address this memory bank is 12 bits as well. Next to the program counter, we have a third register, which is called the Memory Buffer Register, or MBR. MBR, on the other hand, is going to be a register that is going to contain data that we either store in memory or we retrieve from memory, and therefore the size of this register is not going to be 12 but 6 bits. Next, we have probably the most important register in our architecture. It's called AC, and is known as the accumulator. The accumulator will be the register we use to perform operations and store temporary results. Now, the interesting part here is we're going to have as well the combinational part ALU, which will be in charge of performing arithmetic and logic operations, as we saw in previous examples. We have 2 additional registers, in and out reg, which will be used for input and output operations, and a final register, which will be IR, which we will call the instruction register. Now let's look, now that we have introduced only the names of these registers, let's see how are they connected to each other. And the crucial observation here is that this architecture, all these blocks are connected through a bus that we are depicting like this, which contains address and data bus. And the connections of these blocks to this bus are all of them like this. R is connected like this as well. PC, program counter, can write on the bus or read from the bus. Same thing for MBR. Same thing for the accumulator. What this means is that all these registers can write on that bus or read data from that bus. And therefore, we don't need so many point-to-point communications. Okay. Additionally to these connections, we still need to see how the data comes in and out of the ALU. Now, this architecture, it's going to rely mostly on the data that comes from memory and is stored in MBR. Processing the operations will be in the ALU, and storing the results will be on the accumulator. Therefore, we're going to have in this architecture these additional specific connections. So we'll have the possibility of loading data from the MBR to the accumulator and vice versa. And the ALU will be capable of taking 2 of MBR and accumulator and store the result as well on the accumulator. So if you look a bit carefully here, these 2 registers, they have to be controlled in a way that even though they have 2 possibilities to read their data, In the case of the accumulator, we have 3. There has to be some control logic that has to decide at all times if the accumulator is going to load whatever value is in the bus, whatever value comes from MBR, or whatever value has been produced by ALU. Now, the communication of all these blocks to the bus, we're going to enumerate them like this: 1, 2, 3, 4, 5, 6, 7. You have to remember that only one of these connections can be active at the same time in order for the value to propagate to the entire bus. Remember that a bus is a collection of signals such that if 2 connections are connected at the same time, that produces an unstable value all around the bus. So we need a policy to access the bus such that out of these 8 connections you see here, only one of them is active at any point in time. So now let's go over again the size of the registers we have. These 2 registers, MAR and PC, they have memory addresses, represent like this, and therefore the size is 12 bits. They have memory addresses because this is when the register that we're going to use to store the address to access memory, and the program counter is always pointing to the address of the next instruction we have to execute. MBR and AC, on the other hand, will be processing data. Now the data comes from this memory, and we know that this memory is 16-bit addressable. In other words, it has 2 to the 12 cells, each of 116 bits. These cells, when they are read from memory, they'll be stored in the MBR, and the results will be processed by ALU and stored in the accumulator, and therefore we have 16 bits here for data processing. In this architecture, the additional 2 registers, in-reg and out-reg, are used for input-output operations, and they are based on the representation of letters, and therefore they will have a size of 8 bits for input and output. 8. And finally, this register, which is the instruction register. These instructions will come from memory as well, and therefore, from the point of view of the size, it is similar to the accumulator and MBR, and therefore, you'll have also 16 bits. So, to summarize, what we have here is a very simple architecture. This architecture is based on this first block, which is the memory with data and instructions. And then these registers over here will be used to store addresses for the case of MAR, a counter, what we call the program counter, next instruction to be executed, the data that is being either read or written to memory, MBR, the accumulator for operations will always store the result there, input data into the computer, output data into some sort of peripheral or device, and where we store the instruction being executed, the instruction register.
So we have seen the explanation of the data part, and now can you tell me what is the advantage of point-to-point bus and what is the disadvantage of point-to-point bus? At this point, bus connect different components inside the data path. Can anyone tell? Yes, what is the advantage? Anyone can have some idea or think about the advantage of point-to-point bus?